This is a piece of software that was written by a former student here as part of Mr. Wallace's class. It is very well done, it is very accurate, and I would say he has a high likelihood of being able to sell this to either publishers or school districts or things of that sort. But the main thing here is to talk about the shapes that we can't draw three-dimensionally. That's the key with this. So what we have is we have the nucleus here. This is the protons and the neutrons as they get added down here. What we're showing here is the first level. Now you remember from class, the first level is essentially 1s. So if I go up here, I have the 1s shown with this sphere. Now half of it is away, half of it's not, and you can see it there. When I take and do the 2s, all I'm doing is getting bigger. So now if you remember from the video, the 2s electrons start here and go to here, the 1s electrons from here to the nucleus. So it's not likely that we're going to find a 2s electron here. It is likely that we're going to find a 2s electron in here. Now I can continue to add s's. 3, of course, is going to be bigger. 4 is going to be bigger yet. So you can see we're getting larger as we go through. 5 is going to be bigger. 6 is bigger. And 7, this is your largest level here. Now, as you can tell, the space gets larger as you go across. So the goal of quantum mechanics with the P, D's, and F's is to divide this space into smaller pieces so we can say this electron's here, this electron's here, but it's still only a space. Now I'm going to take off some of these S's because we want to start to deal with the actual shapes inside it. Okay, now P you also know the shape of. So here's a 2P. You can tell it's a dumbbell shape. You got the lobe on this side and lobe on this side along this axis, the red axis, whether it's the X, Y, or the Z. Okay, I'm not sure he labeled the axis.
Oh, it's X. It says it on the P orbitals. Yeah.
Where?
When you go to P orbitals.
Okay, so that is the X. The Y is going to be your vertical here, and then the Z, you're going to have those three shapes sticking out. Now, why do they stick out farther than the 1s? Because there's spaces in the 2s that's supposed to be taken up. The 2s, if we superimpose it, will be the same distance out as the 2p. So if we take the 2s, these distances are the same all the way across. Now the one thing quantum mechanics doesn't explain yet is how I can get an electron from here over to this side, because technically they don't connect. If you see, let me take the 2s back out. You can tell they're not continuous through here, so we're not quite sure how they get from one side to the other, or if they do, for that matter. So that's the shape of a P. I'm going to take the P's out for a minute. Now the D's are in between the P's. So this is the first D. You can tell because the P's were along the axis. This is the area in between it. So you got the D's here, the D's there, the D's there. So those are the easy ones. Those are the easy D's. Now, this is a harder D. This is between, as he describes it in the computer program, x squared, y squared, and then this is the last one that, again, is fairly difficult. You have the donut shape here with the two axes coming out. Very rarely do we talk about that shape because it's so uncommon. So if I were to add all of the D's, okay, now that's a bunch of pieces. There is space in there for the 3 P's that isn't covered yet. So if I were to add the 3 P's to this, you have that space, and that space that isn't covered yet. And then guess what? You have the 3S that this all fits inside, that there's spaces in the 3S that isn't covered yet. Now that's as many divisions as the 3 can have. If we get bigger to the 4s, you can get the 4th division. So let me take the P's out of here. Okay. Now these are the shapes that, I said in the notes, don't worry about, because until now, frankly, there wasn't a way for us to do it. So these are 4. These are pretty big. Okay, I'm going to see how it goes. Here's the first one. So this is y to the 3rd, x to the 3rd, yz to the 2nd. So let me click off these. That's yz to the 2nd, xz to the 2nd, and zx to the 2nd. So these 3 are related to each other. And then you have xyz. So you can tell it's got this superimposed picture here. And then z to the 3rd is that donut hole again. So you got
2 donut holes?
there. You got 1 here. Yeah. Let me change the dimensions of this. Whoops. See, you got the sphere there and the sphere there.
That's awesome.
Okay.
Yeah,
So now technically, if we put all of the F's, there are still spaces in there that aren't taken up because there's the 4 D's here, 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 and here. There's the 4 P's here, here, and you got the one up there. And then guess what? We have the S, which superimposes the whole thing. The bigger the space, the more divisions we have to have in this whole thing.
You put all of them on there. Like
Put all of them on there?
Yeah.
Well,
Has like kind of a donut, like a sprinkle.
okay.
Got on her donut.
So that's 7.
We should do a donut lab.
And then
Which one is tasty? Please do.
Name them after elements. Make it relevant.
so you can see the P's coming in. These are the actual, again, that's why most people will draw the P's because they're easy to draw. We're so big now that you can't even see the 3rd layer because the nucleus is so close. And all right.
Dang.
So that is the entire divisions of the atom.
Looks like a lot of balloons connected to each other.
It looks like up.
Well, and the key is there's no space of the atom that isn't classified. That's the key, is there's no given space that doesn't have at least one defining characteristic.